Many of us whip out our phones, open Spotify, and play a song, while trying to comprehend calculus and figure out how the last long quiz went wrong. I've heard one too many students ask out loud, why do complex mathematics exist? Why do we have to study how lines bend or how particles go? Why isn't sine a sin? What many of us do not realize is that, without any of those things, we wouldn't have much of the cool stuff we live with nowadays. Even the songs playing on our phones. Back in the 20th century, computers had started to develop rapidly as computational tools, but scientists were also exploring alternative uses for computers beyond statistics and wartime cryptography. They knew that, as long as there were mathematical models for something, it could theoretically be attempted on a computer. A particularly interesting application is music. They realized that they could represent signals using numbers, and that they could recreate sound waves using mathematics. If you're wondering how sound is stored on a computer, it's all in the form of numbers. Put them together, and you can graph a wave. But you might be wondering, how does one account for the change of pitch and loudness? How does this turn into this? To simplify things, we will focus on a primitive kind of wave, the sine wave. The sine wave has many useful applications, but what many of us don't know is that as a sound wave, it sounds like this. Sine waves can be sound waves because sound is produced via oscillation, or in simplified terms, the bouncing back and forth between two states. This is why we hear sound when things vibrate. Sine waves are perfect examples because the sine function is a periodic function. It repeats itself over a certain period, going from peak to peak, and the repetition goes on infinitely. There are three important things to note when graphing sine waves: period, amplitude, and phase shift. The period is the distance between two peaks. The amplitude is the height from the center line to the peak. Lastly, the phase shift is how far the function is from the usual graphing position, but we will ignore that for now since we're trying to show a simplified model. You may be wondering, what exactly is the connection to sound? Well, the graph of a sine wave is the representation of a sine-shaped audio wave. Recall that sound waves are higher pitch at higher frequencies, and that the frequency is higher when the wavelength is shorter. The period is the wavelength. Reduce the period between peaks, and the resulting sound is higher frequency, or higher pitch. Widen the distance between peaks, and the resulting sound is lower pitch. Recall again that sound waves are louder when there is more energy. Amplitude is equivalent to the level of energy. More current is used to generate sounds with higher amplitude, or in electronics terminology, gain. When you increase the amplitude, the volume of the sine wave increases, so I have to speak louder for you to hear me. Better. But yes, basically, we play with the graphs of waves, or in mathematical speak, transform the functions to manipulate the resulting output. There's actually a mathematical equation for the manipulation of sine waves. This is y equals a sine parenthesis open bx plus c parenthesis close plus d. If you take away the variables for phase shift, this is our equation. Y equals a times sine of bx. A is the amplitude, while b is the period coefficient. The equation for the period is 2 pi over p. There's also a version of this equation used by researchers in acoustics, which is y equals a times sine of 2 pi times f, wherein f is the frequency in terms of hertz. Hertz being how many oscillations per second, or how many periods there are in 1 second. Let me show you some functions and the expected sound. I won't make the amplitude very accurate to protect your hearing, but here goes. But as convoluted as this may seem, this pales in comparison to the sound waves of actual music. This is awfully impractical to graph by hand. If you were to graph how much the rate of change of variables A or B accelerated or decelerated, you would still end up with a very complex graph. But nevertheless, it shows you how complex mathematics can get, and how computer scientists and engineers had to deal with this in order to make audio devices, like the speakers on your phone, possible. So the next time you study while listening to Spotify, don't bother asking why complex mathematics exist, because if they did exist, your phones and the music coming from them wouldn't too.